We are beginning Unit 6 in this video, and the topic here is rational functions, which again is an entirely new function family. When you think about a rational number, you think about something that can be expressed as a fraction. A rational function is simply an algebraic expression in the form of a fraction, and in fact sometimes they're even called algebraic fractions. So let's take a look at our first section here, 6.1. We'll be looking at different representations. Again, we're going to go back to the numerical, the graphical, and then finally the algebraic expressions or the analytic. And we'll kind of take a look at all of these as we go through this section. So first of all, a rational function here in the form of this algebraic fraction looks like p of x over q of x, where p and q are both polynomials. So notice polynomials, those are just powers of x, right? You're not going to see any exponentials or any logs here. We're going to start by looking at a simple analytic form, f of x equals 1 over x. We'll take a look numerically with a table of values at what that looks like, and then we'll plot the points on a graph so we can see all three representations together. So first of all, my function f of x is 1 over x. So I'm going to start over here. If x is 4, that's just 1/4. When x is 3, we've got 1/3, 1/2. 1 over 1 is still 1. And remember that when you divide by a fraction, it's just like multiplying by the reciprocal. So 1 over 1/2 would be the same thing as 1 times 2 over 1. And that just gives me 2. Same idea here. Dividing by 1/4 is the same as multiplying by 4 over 1. Just going to give me 4. Be careful with this one. What happens when I take 1 and try to divide it by 0? Well, division by 0 is undefined, right? So 1 divided by 0 does not exist. And so we're going to have to look at what that means when it comes to graphing and how that's portrayed on the graph in just a minute or two. All right, 1 divided by negative 1/4 would be -4. 1 divided by negative 1/2, -2. 1 divided by -1 is -1. 1 over -2 is -1/2. Here I'd have -1/3, and here I'd have -1/4. So let's go ahead and plot those points. You'll have to estimate the fractions just a little bit. I'm just going to put something in here so I don't get my marker on the next page. All right, so starting with 4, 1/4 would be, let's see, that's 1/2, so 4 1/4 would be about here. And so on. Go ahead and plot these points. All right, hopefully you came up with something like that. And remember that at x equals 0 right here, the graph doesn't exist, so I won't have any actual point at x equals 0. If I just kind of connect these with sort of a smooth curve, looks like that. And based on the things that we've seen in the last chapter or two, it looks like this graph is getting really close to, or as an asymptote, the y-axis. In fact, that's exactly what happens. The graph approaches the y-axis, but doesn't actually touch it, because again, there can't be any point at x equals 0. I'm seeing that same asymptotic behavior over here. These y values are getting smaller and smaller. They're approaching the x-axis but not touching it. And then down here I have very similar. We're approaching the x-axis on the left side and then going down to approach the y-axis in the middle. So notice this time we have a graph that actually has two asymptotes. The vertical asymptote here on the y-axis, and then the horizontal asymptote here on the x-axis. So let's document those. Our vertical asymptote is the y-axis, or in other words, x equals 0. The horizontal asymptote was the x-axis, which would have equation y equals 0. All right, there are no intercepts, right? Because the axes are asymptotes, we never cross them. So we have no x-intercepts, no y-intercepts. In terms of the domain, if we think back at our numerical table of values, we saw here there was a problem when x was 0. X cannot be 0, so my domain is basically all real numbers except 0. If I wanted to write that in interval notation, I could write it as -infinity to 0 with a parenthesis, joined with 0 to infinity. And notice I've got everything in there except because of the parentheses, I've just kind of skipped over the 0. When I look at that in terms of the graph, I see for all of these x values I can find y values, except right here at 0. There is no y value on that y-axis. And then once I get past 0, I can start finding y's for every x again. If I go the other way and ask about the range and think about the y values, notice there are y values all the way down through here, with the exception of when I get to y equals 0, the x-axis, the graph never touches it. So y is never equal to 0. Then we start getting more y values down here again. So my range is going to be very similar to my domain. It's all real numbers except 0. Or I could write that again in interval notation. By the way, instead of writing out all real numbers except 0, you'll often see it written this way. In this case, it's a range, so we're looking at y values. Y is a real number, that's just sort of shorthand. Y is an element of the real numbers, such that y is not equal to 0. Here I could have written, since it's domain, x could be any real number. It's an element of the real numbers, such that x is not equal to 0. So just a little bit of new notation there, but another way of writing the exact same thing. All right, well, now that we know how to graph our most basic rational function, what about other rational functions? We can, once again, use all those same transformations that we've already used 3 or 4 times this semester. If we consider our parent function, f of x equals 1 over x, and we transform that parent function, the most important pieces that we want to transform and get in the right spots would be the horizontal and vertical asymptotes. Once I know where those are, it's not very difficult to just kind of sketch the shape of that graph around those asymptotes. So as long as I place the asymptotes correctly, I think I can draw that shape. All right, again, we already know what happens with these. Let's just quick look at the format for our rational function. Parent function f of x equals 1 over x. If we have a multiplier of a, I'm going to have, let's see, if I multiply a times 1 over x, I could actually just multiply the a times the 1 in the numerator, so it may just look like a over x. Either of those formats really means the same thing. And of course, we already know that that's a vertical stretch if the a value is bigger than 1. And it's a vertical shrink or compression if the a value is smaller than 1. And I am assuming that a is positive here. We talk about what happens with a negative in the next line, right? All right, so if I do have a negative in front of the entire function, that would look like negative 1 over x. Could also be written as negative 1 on top over x. Again, whether I put the negative in front or on top, it means exactly the same thing. By the way, you actually could put the negative on the bottom as well, although you rarely see that happen. But only one negative, not negatives in multiple places. This, of course, is going to reflect our graph across the x-axis. All right, there's our two horizontal shifts. If I replace the x with x plus h, I know my graph goes to the left h units. And if I replace the x in the parent function with x minus h, we've seen before that that's going to shift our graph to the right by h units. And then the last two are our vertical shifts. If I take my whole parent function, 1 over x, and add k, I'll be shifting my graph up by k units. And again, if I take the whole parent function, 1 over x, and subtract k units, I'll be shifting my whole graph down by k units. So, very much the same types of shifts that we've seen a number of times before. Let's practice those in the context of these algebraic fractions or rational functions. All right, our first one here, 1 over x plus 2 minus 3. My horizontal shift here is left 2. Oops, I don't know why I left that big space. Let me try that again. Left 2. And my vertical shift here is down 3. So what I'm going to do is I am going to go ahead and I'm going to graph my asymptotes first. Left 2 means the vertical asymptote moves left 2. Down 3 means my horizontal asymptote moves down 3. I can actually jot down what those vertical and horizontal asymptotes are right now. My vertical asymptote then is now at x equals negative 2. And my horizontal asymptote is now at y equals negative 3. I'm going to go ahead and again, just a quick reminder, what I'm drawing is that parent function. I'm going to draw right around the asymptotes. And without any kind of vertical stretch or shrink, notice that 1, 1 and negative 1, negative 1 were on the graph. So what I often will do here is from this sort of new center point, I'll just go, okay, over 1 and up 1, and draw my graph approaching the asymptotes. And again, from the center, left 1 and down 1, and draw my graph approaching the asymptotes. It's not absolutely necessary in terms of precision. I'm not asking you to be that precise, but it actually does help me a little bit, just gives me kind of a starting point or a place to draw. So I tend to use that if there's no vertical stretch or shrink. In terms of domain and range, the x values are never -2, right? They never hit that x equals -2. So in terms of my x values, x cannot equal -2. And the y values never hit the -3. So y is not equal to -3. So notice once you have your vertical and horizontal asymptotes, the domain and range are very directly related to those. If I wanted to be a little bit more mathematical about this, I could write them in interval notation. From -infinity to -2, and I kind of jump over that -2 and go from -2 to infinity. And same idea here for the range. I could go from -infinity to -3, hop over that -3, and then go on to positive infinity. All right, let's try the other one. This time, I definitely see my horizontal shift to the right 1. And then because of the negative, that's going to be reflected across the x-axis. So in terms of my asymptotes, I'm moving right 1, so my vertical asymptote is going to go right 1. But I haven't moved up or down at all, so my horizontal asymptote is going to remain on the x-axis. Let's go ahead and sketch the graph right now. Again, I'm just going to go kind of 1, 1. Whoops, I'm so sorry. I didn't reflect. Right? Normally we think of it this way. If I'm going to reflect that across the x-axis, instead of being up here in the first quadrant, this is going to go down here to the fourth. And again, instead of being on the bottom on the left side, it's going to be on the top. Like so. All right, my vertical asymptote is here at x equal 1. And my horizontal remains here at y equals 0. My domain, the x values never touch the x equal 1, so x is not equal to 1. And the y values never touch 0, so y is not equal to 0. And I'll leave you to write the interval notation if you'd like to try to do that as well. All right, we've been talking a little bit about domain in terms of the graph and how it's shifted left, right, up, and down. But algebraically, there's a fairly simple way of determining the domain for even more complicated algebraic fractions than those that we've looked at so far. It goes back to the idea that we can't divide by 0. So if I have an algebraic fraction, I can't allow the denominator to be 0 because that would indicate division by 0. So in any rational function, we cannot allow the denominator to equal 0. It would make the function undefined because we cannot divide by 0. So if I ask you to find the domain of these functions, what you want to do is you want to focus on the denominator. You want to say, well, I know I cannot let 3x plus 2, in this case, cannot be 0. So 3x cannot be -2, and x cannot be -2/3. Now I am going to say that it's okay with me if you take a shortcut here. I know technically this means the domain is from -infinity to -2/3. and then from negative 2/3 to infinity. But just to avoid having to write that all out every time, we'll agree amongst ourselves that if I write x is not equal to negative 2/3, what that really means is x can be any other real number. We'll just take that shortcut as we go through these. All right, in B, my denominator is the x cubed, so I simply have to say that x cubed cannot be 0. And the cube root of 0 is still 0, so that just means that x cannot be 0. In C, this time I've got a whole quadratic in my denominator, so I'm going to have to say that whole thing cannot be 0. And let's see, I'm going to try to factor that, hoping it does here. I would need a sum of 8. And in my product, 12 times negative 15. My product has to be negative 180. If you'd like to play around a little bit with that with your calculator and see if you can come up with those numbers, go ahead and pause right now. Otherwise, I'm going to say I think it's 18 and 10. I would have to put the negative on the 10 to get that to add up to positive 8. So I do not have a leading coefficient of 1. I'm going to have to use the extended method here. So I got my 12x squared plus 18x minus 10x minus 15, not equal to 0. And I'll factor out a 6x. Gives me 2x plus 3 here. And then the second pair, I'm going to factor out a negative 5, which also gives me 2x plus 3. So I've got 2x plus 3 times 6x minus 5. Cannot be equal to 0, meaning 2x plus 3 is not equal to 0, and 6x minus 5 is not equal to 0. See, I'll do a little step in my head here because I'm running out of space. X can't be negative 3 divided by 2. And here x can't be, see, it'd be positive 5 divided by 6. So technically I'm saying the domain is all real numbers except for those two values. Can't use those two values because those would put a 0 in my denominator. All right, and then in D, my denominator is x squared plus 9. And I can't allow that to be 0. Now if I tried to solve that, that would say x squared is not equal to negative 9. And if I take the square root, remember we haven't done these for a little while, plus or minus the square root of negative 9, it's negative, so those are going to be imaginary, right? Plus or minus 3i. Now, at least for our purposes in this class, and for most of the math that you would see for a number of years yet, we really wouldn't be worried about using imaginary numbers in the context of an algebraic fraction. And so we're going to go ahead and say, since the only bad values are actually imaginary numbers, that means that all real numbers are perfectly fine. So when I list my domain, I'm going to say it's all real numbers. Or I could list it as negative infinity to infinity. The only problem numbers were imaginary. I'm only considering real numbers for these algebraic fractions. All right, we have one more topic, I think, here in this introductory section. I want to talk a little bit about simplifying rational functions or algebraic fractions. And simplifying in terms of a fraction is really just a matter of reducing it to what you've probably called lowest terms or simplified form when you're doing with numerical fractions. What I'd like to point out or remind you of is the thought process that goes into simplifying a numerical fraction. Let's say you have 12/15ths, and you want to reduce that to lowest terms. Although you probably do these steps very quickly in your head and don't think it through, this is what's really happening. You start out by thinking, okay, 3 goes evenly into both 12 and 15. 12 is 3 times 4, and 15 is 3 times 5. And I can actually rewrite that by separating the factors. I can write it as 3/3 multiplied by 4/5. Since 3/3 is just 1, and 1 times anything is itself, I end up with that 4/5 as my simplified form. Now what I really want you to notice here, and this is super, super important, is that the only reason this worked was because there was multiplication here, right? This was 3 times 4 and 3 times 5. So I could separate it into 3/3 multiplied by 4/5 and 1 multiplied by 4/5, which then gave me the 4/5. That would not have worked if I had separated these into addition or subtraction problems or something like that. It was super important that they had to be multiplication, or I wouldn't have ended up with that 1 times anything is itself. We have to apply that same idea to our algebraic fractions. We will not be able to simplify them if we have addition and subtraction going on in the numerator and denominator. It's going to have to be multiplication, which means it has to be factors or factored forms that we use. So once again, what was the key to the success here? The key to making this process work was that we were working with factors or multipliers. Right? That means that when we try to simplify an algebraic fraction, we must use the factored form, both numerator and denominator. We can only reduce our fraction by reducing factors, never by reducing add-ins. Right. All right, so let's go ahead and see what we can do here. We'll do some simplifying. As I look at this first one, the numerator, really, I can't do anything with that. So I'm going to leave the 4x squared just the way it is. But in the denominator, I could factor out a GCF of x squared. When I do that, I get 7x plus 4. Notice that now this is 4 multiplied by x squared. This is x squared multiplied by 7x plus 4. So I do have those multipliers, which I can divide out. Okay? I won't always write out this step, but I just want to show you. If I wanted to, I could separate that out as x squared over x squared multiplied by 4 over 7x plus 4. X squared divided by x squared is 1. And 1 times anything is itself. Now, usually we don't take the time to actually write out that whole pulling out the x squareds and changing it to a 1. What we usually do instead is take a shortcut and say, well, x squared divided by x squared is 1. 4 times 1 is 4. And 1 times 7x plus 4 is 7x plus 4. So we usually go straight from here to here. But I do want you, at least in the back of your mind, to recognize what's happening here. When we say we cancel, and I really don't care for that word because it can mean so many different things, but when we kind of casually say we're canceling the x squareds, what we really mean is we're dividing them to get a factor of 1, and we know that 1 times anything is itself. Let's look at where we are with this problem right now. Look at those 4s. Could I reduce this some more? Could I go ahead and divide out those 4s? The answer is no. Why? Because 4 is not a multiplier. 4 is being added down here. And we never cancel addends. We must work always with factors or multipliers. So this is done. All right, let's take a look here at B. Lots going on, but I recognize right away all addition and subtraction. So there's no way that I can start to reduce my fraction yet. I must get this in factored form. The numerator I think I can do right here. This is a trinomial, so I'm thinking product and sum. Sum of -3, product of -4 would be 1 and -4. And because I do have a leading coefficient of 1, I can take advantage of my shortcut here. X squared has to be x times x. And then I'd have the +1 and the -4. The denominator is going to take a couple of steps. I notice here that with the 4 terms, I'm going to have to go with factoring by grouping. So I'm going to just kind of do the factoring off to the side so I don't kind of muddy up my problem. So doing my grouping, I'll factor an x squared out here, which gives me x minus 4. Plus I can take a 3 out there, which also gives me x minus 4. So my factored form would be x minus 4 times x squared plus 3. So I'm going to put that in my denominator. All right, I do have a factor now. These are multiplied here. These are multiplied here. So the x minus 4s are factors. I can say x minus 4 divided by x minus 4 is just 1. And 1 times anything is itself. So I just end up with x plus 1 over x squared plus 3. Again, I don't want to be tempted to simplify this any further. These are addends, so I cannot do any division with the x and the x squared. They're not being multiplied, they're being added to their respective pieces there in the numerator and denominator. All right, we have a last couple of examples, and they both revolve around kind of a special case, but one that can be handy to recognize. If you look at C here, 4x minus 9 over 9 minus 4x. That numerator and denominator are very, very similar to one another, but they're not quite the same, right? The subtraction is reversed in the denominator compared to the numerator. What I'm going to do is I'm going to, first of all, keep the numerator the way it is, and I'm just going to rewrite the denominator in descending order. I'm going to call it negative 4x plus 9. Okay. Next, I'm going to factor a negative 1 out of my denominator. So keep the numerator 4x minus 9. And in the denominator, I'm going to factor out a negative 1, which makes that a positive 4x, and makes that a negative 9. Now notice, the negative 1 is multiplying the 4x minus 9. So I really am allowed to reduce 4x minus 9 divided by 4x minus 9 is 1. 1 divided by negative 1 is negative 1. Anytime you have this situation, the same 2 terms being subtracted, but the subtraction is reversed in this way, this process would work and you'll get negative 1 every time. So oftentimes when we see this, rather than going through all this, because we're kind of in the back of our head saying, hey, I already know that, we'll say, hey, yes, I can reduce, but I know when I reduce these with the terms reversed, instead of dividing out to positive 1, they divide out to negative 1. So we'll see that in context in the next example. All right, looks like I've got a bit of work to do here on the factoring on both top and bottom, so I'm going to kind of create some space for my factoring over here on the right-hand side. Only 2 terms, and I'm kind of recognizing that as a difference of cubes. That would be 1 cubed, subtract 3x cubed. So u is 1, and v is 3x. And I'll just remind you the difference of cubes formula looks like u minus v times u squared plus uv plus v squared. So u minus v is 1 minus 3x. U squared is 1. Plus u times v is still going to be 3x. And when I square that 3x, I'm going to get 9x squared. So I'm going to put all of that into my numerator. All right, denominator. Let's do a little bit of work on that one. This time I have a trinomial, so I'm thinking sum and product, sum of 7. And the product here, 15 times negative 4 would be negative 60. Let's see, thinking probably 5 and 12. If I make the negative 1 be the 5, that'll add up to a positive 7. And I do have the leading coefficient that's not 1, so I'm in my extended form here. 15x squared, we'll rewrite the middle as negative 5x plus 12x minus the 4. And then we'll do grouping. Factor out a 5x, and I get 3x minus 1. Plus, over here I could factor out a 4. I'm also going to get 3x minus 1. So I have 3x minus 1 times 5x plus 4. And I'll put that in my denominator. All right. Now that I've got factored forms, again, I won't write them this time, but it is multiplication, right, in between those parentheses. So they are factors, and I am allowed to reduce. I'm going to look at this and say, you know what, this looks a whole lot like the problem that we just did up there in C. I have the same 2 terms being subtracted, but the subtraction's been reversed. So I'm going to say, yes, I can divide those out, but instead of dividing to 1, I know those actually divide to negative 1. There's a couple of different things I can do with that negative 1. One option is I can just put the negative in front of the entire fraction, like this. And that's just fine. It means the same thing as any other way of doing it. Another option that I have is I could take that negative 1 and I could distribute it through the numerator. And I'd get negative 1 minus 3x minus 9x squared over 5x plus 4. Those are both pretty popular ways of writing the answer. Technically speaking, it does not matter whether I put the -1 on the top or whether I put it on the bottom. So another option would have been to actually distribute it through the bottom instead. You rarely see people do that, but I just want to show you all the possibilities here. So this time the numerator would have stayed the way it was. And I would have ended up with a -5x and a -4. All three of those answers mean exactly the same thing. A negative in an algebraic fraction can be put in the front, it can be put on the top, or it can be put on the bottom. But you can only use it once. Don't do both top and bottom, for example. That would be two negatives, and that would make it back to a positive, right? All right, so that's our introductory section here on algebraic fractions.